All right, so let's do an application, and I think we have just enough time to do an application. Uh, and the application we want to do is a very famous application. It's the blackbody radiation. It is the problem that gave birth to quantum mechanics. So what is blackbody radiation? So a black body is an idealized object. So it's a perfect absorber of radiation. And you might say, why are we considering a black body instead of, say, a particular body? So the problem is, if you want to consider the radiation emitted by a particular material, you are going to be asking questions about the atomic structure of that particular material. Whereas the problem that we are dealing with is not, it's a more generic problem. So we assume that, so according to quantum mechanics, every material, every atom has its own spectrum, right? And therefore, it's if you, when you heat it up, it's going to radiate in frequencies which is very particular to that object. So whereas that what we assume about the black body is that the black body is essentially it's made out of some oscillators and which are essentially quantum mechanical oscillators. And when you heat up a black body, it emits a radiation that is very, very specific, that is very specific to the temperature, So it depends on the temperature, and it was something that classical statistical mechanics failed to describe in a spectacular fashion. So according to classical statistical mechanics, the radiation energy, let's say, or energy density, emitted by a hot black body is infinite, which is a nonsensical result. And Planck realized that the way to solve this is to assume that the atoms which you can use to model the molecules or the oscillators that you use to model the molecules and the atoms of the wall of the black body, their energies are given by, they are quantized in units of some constant, which now we call h bar, and omega is the angular frequency. Of course, I think Planck used h nu. Nu is the frequency, and h is what is known as Planck's constant. But now in modern notation, we use Dirac's h, which is h bar. So this is now called Planck's constant, okay? And you will recognize this formula from the tutorial on simple harmonic oscillator. The simple harmonic oscillator, the energy levels were n plus half h bar omega. When the energies are large enough, you can ignore the half, which is the vacuum energy, and this is exactly what this is. Okay. So Planck, of course, had no basis, physical basis to assume that. And so he was very, very shocked that he had to assume something so radical. And it was only after the development of the new quantum mechanics by Schrödinger, Heisenberg, Dirac, and other people that this was justified. So, of course, we are not going to take the historical route in deriving the blackbody radiation energy intensity. We are going to use statistical mechanics, and one thing that we need is what we are going to, deal with. We are going to treat the black body as a gas of photon in equilibrium at some temperature 1/beta. Okay, that's what we're going to do. So what we will need is what is the energy of a photon whose frequency is omega. And that is given by quantum mechanics h bar omega. This is something that Einstein proposed in explaining the photoelectric effect, another famous historical experiment. So that is basically what we are going to use here. The other thing that we will use is that the photon numbers are not conserved. Number of photons are not conserved, okay? This is something we all know and see every day. Whenever we turn on light, a switch, we see photons being created. When we turn off the switch, we see that, the photons that were created have been absorbed. So the number of photons are not conserved. So for the so if we are going to write down the partition function for photons whose frequency is omega, we have to consider the case of 0 photon. We have to consider the case of 1 photon. We have to consider the probability of 2 photons, so on and so forth. Now, this is a geometric series which sums up to 1/1 minus e to the power minus beta h bar omega. So this is the partition function for photon of frequency omega. Now, photons don't interact, at least at the quantum mechanical level. They do interact when you take into account quantum field theory, but that's a much, much weaker effect, and we're not going to go into that. Is that we have to, like all photons of different frequencies. So photons of different frequencies are independent. So the total partition function is going to be a product of all these different photon frequencies. So in other words, if I take the log of the total partition function, I can just do the sum, because multiplication upon taking logs become addition. So our frequency will be d omega, and there will be a density function, which is something that we just developed, and then z of omega. So this is going to be the partition function for the photons. So g of omega is something we know. We know it as g of e. So we know as g of e d of e, and that is going to be v e squared by pi squared h cubed c cubed d of e. Okay, so now we use the fact that E is h bar omega for photon, and then we can write this as g of omega. This is an abuse of notation because g of omega is not the same function as g of e. So you can put a tilde here if you like. And this is going to be, here we have v, and then we have h bar squared omega squared, that's e squared. divided by pi squared h cubed c cubed. D of E is going to be given by h bar d of omega. And so we get that these guys will cancel out, and we will have v omega squared by pi squared c cubed d of omega. So this is our g tilde of omega, okay? So we get our partition function, which is log of z, is going to be, well, yeah, sorry. So it'll be a minus sign, and you'll see why the minus sign, and then 0 to infinity d of omega. And then this factor we just derived, v omega squared pi squared c cubed, and then log of 1 minus e to the power minus b h bar omega. So this was in the numerator, and we raised it to the numerator, and that's why we have a minus sign here. Okay? So what is the energy? The energy of the system is given by minus log of z by the derivative of log of z with respect to beta, right? So now we can just do this, and we get an integral from 0 to infinity, and then v omega squared divided by pi squared c cubed h bar omega. This is yeah, this is coming from from taking the derivative with respect to beta of this guy, and then we have something in the denominator, and then we have d of omega, and we can simplify this. So this is, we can call this the Planck distribution. What is the Planck distribution? The Planck distribution is how does the energy depend on the frequency, and it is given by v h bar pi squared c cubed omega cubed d omega divided by e to the power beta h bar omega minus 1. Okay, so this is the Planck distribution. Okay. And what does it look like? So, you can convert this to lambda, and that's an interesting exercise that I want you to try on your own. It's actually, people usually make mistakes when you convert it to lambda. And then you have, so here you have lambda, and you have the, the energy density, or the energy or intensity, and then you have something like this. So this is some temperature, say at 6,000 Kelvin. And if you lower the temperature, there'll be less energy radiated. Sorry, this is not a very good drawing. And the peak, shifts to the right, and then the peak, does something like this, right? So it's the maximum is something that depends inversely on one or more on lambda. Okay, so this is the Planck distribution. So before I make some comments, do we have any questions?
Lambda is the wavelength?
Sorry, yeah, lambda is the wavelength. Yeah. So okay, how does photon make a gas? They're always moving at a single direction. Yeah, that's what I mean by a gas. Is like they're not like, I mean, a gas molecule. A gas has like particles which are moving, right? And photons are just like a gas which is moving at the speed of light. By gas I mean that photons are moving in all kinds of different directions. It's kind of a kind of an atmosphere of photons, if you like. And the thing is that, there is a photon pressure, there is radiation pressure. That's something you've heard of things like, oh, we want to make a solar sail, right? Solar sail can have solar wind pushing it, and it's also the radiation. So radiation, because photons are particles and they carry momentum. Even if you think of it as electromagnetism, and it's radiation still carries energy and therefore momentum. So there is and there will be some momentum transferred. So photon can be thought of as particles. It's just a gas of relativistic particles. That's all. Okay. Any more questions?